homology. So this representation homology is some kind of relatively new invariant for an associative algebra. Out of this associative algebra, you construct certain homology groups, which depends on some integer n, which are called homology representation homology groups. They will try to motivate a little bit where they come from and what they are. But my interest will be in some specific example of like polynomials in two variables or quiver path algebras of quivers with relations. And if you do that, what you will see that some kind of combinatorial identities appear of the type of Macdonald constant term identities, which come because you can compute them in different ways. Compare Euler characteristics, and this is particularly in the case if you have a group action. These Euler characteristics are not just numbers, but they are kind of characters, functions, and this leads to this sort of identities. And so, for instance, and so one motivation was to try to understand from this point of view this Nekrasov partition functions appearing in gauge theory. Okay, so this maybe I should write my collaborator. So this will be based on works we did with many collaborators. Mentioned that there will be Berest, Ramadoss, and later we work with Patotski and Willwacher. They will also report on some recent results in the thesis of my student Giovanni. Okay, so we start from A is an associative algebra. Over say field of characteristic 0, but I will take complex numbers. And then what you would like to study are representations of A of dimension n. So let me just first give some sort of intuitive picture of what that is. So you consider all representations of A in n by n matrices. So you have an algebra, you want to represent elements of this algebra by matrices, and this should become linear and compatible with the product. And so I'm going to say it as a set, but then I want to be more precise. Take my algebra homomorphism from A to n by n matrix. Okay, so this is what. So I think this is a colloquium, so I should not assume anything. So this is what is called an affine string. What it means is that you are really care about the functions on this space, and I will give these functions, the polynomial functions, the regular functions, is what we are interested in. So there will be an algebra A sub n, which will be the functions on this Ecran population. And this is what we define. And then Ecran is constructed a spec of that commutative algebra. So I will describe this in the examples, but let me just give the official definition to be precise, is that so this function from A to An is called like this, is left adjoint to n by n matrices in B. So you have, what does it mean? It means that you have to consider algebras over C, and you have this. Until you have commutative algebras. These are associative algebras, you have commutative algebras. So out of a commutative algebra, you can construct an associative algebra by taking n by n matrices with coefficient in the commutative algebra. And then there is a unique kind of left adjoint, and this defines AN. But then we will see what it is in examples. And right, so this is kind of definition by universal property, and then you have to show that it exists. And then what you also notice is that if you have such a representation n by n matrices, then you can construct new one by conjugation by a matrix, right? So you have an action of GLN, an exchange of bases, if you like. And what you are also interested in is the character variety, which will be n, the quotient by categorical quotient by the group, which is GLN. And so, namely, so in terms of algebras, the functions on the character will be just the invariants of the invariant functions. So, okay, so let me give a couple of examples of what we are interested about. So one is the first example is easy, kind of. So you take just polynomials in one variable. So this is a commutative algebra. You do it as an associative algebra, and you want to see what are the representations of this algebra. And of course, to give a representation, it is enough to give the image of X of this unknown, and which is an n by n matrices. So rep n will be n by n matrix. And just in a fine space, very simple. And again, the algebra function on it will be polynomial functions of variables xij of the matrix entries ij from 1 to n. And okay, this is kind of first example. Then the second example, which is one generalization of it, is a free algebraic generators. And generated by x and y. So you take linear combination of words in x and y, like x, y, x, or so. And then representation is given if you give two matrices, right? So you will have A that n will be pairs of matrices, and so AN. The polynomial algebra is in two sets of variables. And now the third example, which will be kind of a main actor in this story, will be polynomials in two variables, x and y. So here, this is really a quotient of the free algebra by one relation, which is that xy is equal to y. So you quotient by the decided idea of this relation, right? And so to give a representation of this algebra, you have to give two matrices, x and y, but they must commute. This will be this relation. F8 is what is called the commuting scheme. So it's pair of commuting matrices. And variant matrices. And so the functions on it will be generated by matrix elements, matrix entries, xij, yij, as before. But then you have to quotient by the relation that these two matrices commute. So you have some xij yij minus yij is equal to 0 over 2. Okay, so this is a kind of singular scheme. And so anyway, so these are the three examples, and a fourth example, and then this will be all the examples we will consider. And so maybe a remark is so there is a notion of smoothness for associative algebras invented by Kunz and Quillen, so imitating the definition of Grothendieck for the commutative case. So and so 1 and 2 will not give you definition. Are examples smooth associative algebra. In the technical name is something that turns out to be finitely generated. In the sense of Kunz. Yeah. And and in this case, it is generally true that for smooth algebras, that n is smooth algebraic variety. And indeed here they are very similar, just affine spaces, certainly smooth. And 3 is not smooth. So the commute this polynomial in two variables, of course, is smooth as a commutative algebra, but as an associative algebra is far from smooth. And you see this because the corresponding scheme is single. Okay, so then before I introduce example 4, which is related to quiver, I need to introduce a variant of this story, which is the relative version. Namely, what we consider is an algebra homomorphism. So the basic case is where S is C. It's an algebra over S, but S is also an algebra over C. And V is a representation of S. So V is an S modulo. It is a representation of S, so finite dimension of S. And then you define the representation, the relative. The notation that is used.
Excuse me, is it assumed that S is commutative and
algebra homomorphism, S algebra homomorphism from A to endomorphism. Which means that the image of A should be mapped to LV by this representation. Okay, and so the basic case, the absolute case, is where you have S equal to C and V modular is a vector space. And this is the Ecran of A. And this is useful if you want to do quivers, because if you do representations of quivers, you don't just have one dimension, you have one dimension for each vertex. And this can be understood as a representation.
A question, please. Question?
Is interrupt if you have questions. Okay. Right. So now, so example 4 is quiver. So you suppose you have a quiver. Quiver is a directed graph. We have Q0 and Q1. This is the edges.
The question is whether S is commutative and the map from S to A central.
For the definition, not necessarily, but in the example, it will be so. The example, it will be. The definition, I think, is okay. Right. So, yes, now, so something like that. And so what you know what is a representation of quiver? A representation. So Q, a representation of a quiver. The quiver Q is just an assignment of dimension. And it is a collection of dimensions associated to each of these. What is it? And so it's an assignment. Which edge MJ. So just give some maps, and it's interesting because you have an action of the group. You have a GLN on each vertices, and this acts on the space of representations. And right, and so how to view such a thing? So we will consider this example. Maybe we will impose some relations on this map, quotient by some relations. But we want to formulate it in algebras. Terms of algebra. For that, you look at the path algebra. So this is linear combination of paths. Well, a path from the quiver would be something like this would be a path. You can compose paths if they match. And you declare the product to be 0 if they don't match. So you have an algebra A, which is as a path, and then you have some idempotence, so the EI path goes to 0. And they are orthogonal idempotent. Delta J, 1 or 0. J. And then you can, so then you can take S to be the span. Yeah, so it is indeed a commutative algebra, but it will not be central. So, it's a commutative algebra, and this is the picture. So then better you take V to be direct sum to I. And ER the projection. So EI must be this representation of the projection onto EMI. Okay. And then a representation of Q, the same as the representation of in this. This is a way to let this formally fit in that story, and then you can impose relations, and we do that. And these are all these numbers. See if I say that again. Okay, then there is this story of Berest. So this is the theory of representation schemes. You have, for each algebra, you have a commutative algebra AN, or if you're geometrically a scheme that N. And now, so there are these derived versions. Were introduced by Berest and Khatchatrian. There was a similar construction earlier by Fontaine and Caprano, and but I will use this kind of notion. So one motivation, or their motivation for that, was what is called the Kontsevich-Rosenberg principle. So Rosenberg wrote a paper at some point on kind of non-commutative geometry. So you should think of an associative algebra as describing some sort of non-commutative space, and then you can try to develop some notions of differential geometry or algebraic geometry on this object. We generalize the usual notions in the commutative case. And then what they say is that actually the non-commutative geometry of an associative algebra A should be encoded in the commutative geometry of all this rep n of A for each n. So for each n you have covered associative algebra. This rep n I didn't say, but so this AN are commutative algebras. So you have infinitely many commutative algebras, which are algebras of functions on some scale, and they should encode the non-commutative algebras. And in particular, you have geometric notions like vector fields. So the simplest story would be a vector field. Okay, how to generalize it? So it's a derivation of an associative algebra. Then, if this notion is correct according to that principle, it should induce the same notion on these commutative spaces. So this was kind of the philosophy behind it. And then the philosophy works well in some sense. You can define many non-commutative notions and translate them into commutative notions in this AN. And but they work well if you have a smooth algebra A in the sense of Kuhn-Squillen, because then all these commutative schemes are smooth varieties. But otherwise it's not so good. And so what this author proposed is to go to the derived world to replace your associative algebra by an equivalent, in homotopical sense, an equivalent associative algebra, which is smooth, and then apply the functor to this replacement. So you want some sort of resolution of your algebra A, and for this you need some technology which I will not explain. Let me show you how it is in examples, which is the theory of model categories. So you embed associative algebras in some model category, for instance, differential graded algebras. And then when you have differential graded algebras, there is a notion of cofibrant objects. You replace your algebra by a quasi-isomorphic cofibrant object, which is smooth in some sense, and you apply your functor to this cofibrant replacement, and you get some differential graded commutative algebra. And so their idea was we want to do that. So the idea is replace a quasi-isomorphic cofibrant, whatever that means. Differential graded algebra, maybe you should try DGA, differential graded algebra. A, and then apply, define the derived representation scheme as you apply your functor to this replacement. You expect this kind of derived scheme, but we'll look at mostly on the level of algebras. Then you have to show that it is well defined. Word about why it is well defined. Then we will do it in examples. So what you do is that you extend this. To differential graded algebra. Means to take the algebras with a differential morphism squared to 0 to be a derivation of the algebra. And commutative differential graded algebra. C. And then maybe plus, we take positive degree. So the convention is that the differential is degree minus 1. And so there is such a, first extend it to this, and I will show it in examples. And then this is a model category, so you can replace elements like resolutions. So you have and then you map it to QA. And then you have to show that this is kind of well defined, so it's independent in some sense of the choice of resolution. And the technical reason for that is that this is a so-called equivalent functor. It comes also with a joint. And so it defines a functor on the monotopic category, equivalences, which are quasi-isomorphisms. So this just shows that it is well defined. It is essentially independent from the choice of this resolution. And okay, so then, right. And then by definition, if you take A to be an associative algebra, then you place it as here, you place it in degree 0 here. And by definition, this will be the algebra of functions from the derived representation scheme. So this is the differential graded commutative algebra. So this is the kind of definition of what this is. And then you can define the representation homology. The homology of this complex is differential graded algebra. It comes to the differential and then you are interested in the, and this is an algebra, commutative algebra is homology. And then you might be interested in the kind of character version. So this is the definition of representation homology. Let me explain what it is in examples. So I think that one property that I should mention is that one can prove that maybe story that maybe H0 of A, or the construction, will be the functions from the representation scheme as before, but you might have higher homologies, which reflect the non-smoothness of A, right? And then you have the statement that HR is equal to 0 for I bigger than 0. It's smooth in the sense of equivalent. Okay, so this is the story. And let me explain how it works in the example, because I think it's kind of abstract definition, but you can understand what it is in this example. You can understand that it's not easy to compute if you want to compute. Anyway, so this is the graded commutative. Graded means, commutative means that you have a degree which comes from the homological degree, and all the elements of odd degree are anti-commute instead of commute. Okay, so this is, maybe I should check my time. Okay, very good. Right, so example. So this will be example 3. So example 1 and 2 are given an exercise. There nothing will happen. It's just AN. So example 3, this was the commuting scheme, if you like. So polynomials in 2 variables that you want to view as a pre-associative algebra modulo the relation xy equal to 1 yx. And And so in this case, what you do to construct this resolution is just to introduce some odd variables which kill the relation. So this kind of general principle for finitely generated algebra, finitely presented algebra. We have an algebra with generators and relations. So you start by introducing odd generators whose differentials are the relations. Then you check if you have a new homology appearing in degree 1. If yes, you add more generators and so on. So this is some kind of standard construction. In this case, it's very easy because you will introduce A. Now the resolution will be you take three variables, x, y. It is a differential graded algebra, so you have to give a differential. And you have to give degrees. So these are of degree 0. You start with degree 0, and this is degree 1. And then you say that dx equals dy equal to 0. And this theta is equal to xy minus yx. And so by construction, if you take the homology of this algebra in degree 0, it will be this algebra here modulo the image of D, which will be the relation. So automatically we get the right thing in degree 0. And then you have to check that there are no homology in higher degree order. And indeed, you show that this is enough. It's like a resolution. So you can do this exercise, say, for dual numbers. It's fun to do it. So you have x modulo x squared. Then you can do the same thing. You can introduce theta whose image is x squared. But then you notice that when it creates new homology in degree 1, you have to add one generator in each degree. But in this case, it's fine. It finishes here. And then, so now we can say what is the representation homology. It's represented by differential varied commutative algebra with QA. And so this will be the rep. So the rep, the function on the rep n of it will be represented by such a differential varied algebra. So you have polynomials in variables by j, so the 0, this is degree 1. So I use this notation, but actually it is an exterior algebra in the theta because they're of odd degree. So these are few combinations. The polynomial algebra in these variables times tensor with the exterior algebra in the theta j. And with a differential, the induced differential, and the induced differential is ij, well, ij. 0 and d theta ij. Okay. Yj minus y. You can imagine that it's not easy to describe this algebra, but we will state a conjecture about the invariant part. So if you want to go to the character variety with the GN invariance here, there will be a conjecture. And so we did some computation with a computer on low n, 2x2 matrices, where you can kind of describe it, but it's not. Okay, anyway, this is the one story. So then you have to compute the homology. So then will be an algebra. Okay, so what can we say about this homology? So not much in general, but there are kind of comparison maps to known homology. And so let me give two such maps. One is related to cyclic homology, and let me give an intuitive picture why it works. So let's think of this set N as a set, as a space of representation rho. So if you have a representation rho, N by N matrices, then you can take the trace, right? You can take the trace. And you have A again. Take the trace, and this will be a map really on A modulo the linear combinations of commutations with the cyclicity of the trace, and also is the GLN invariant. So it means that what you will have is you have kind of trace rho. Think of as a map from A to the functions, the invariant function on the representation schemes. For each row you have such a number, so you have a function on the representation scheme, which we call AN. So we have such a map, and this map you can lift it to the derived setting, and what you will get is defined a map from the cyclic homology to the representation. You can compare these maps, and there are cases where this becomes an isomorphism, but there are cases where it is not. So I will not enter too much into the detail because it will not be the focus. So these are kind of comparison maps. We would like to describe another map, which is called Harish-Chandra homomorphism, and this is based on. So again, if you have a representation, then what you can do is to so you have representations of A. Among all representations, you have the representations which take values in the diagonal matrix. To the end, right? F1. F1 to the A, so you get representations of the form one of it. You can do this in very kind of extreme thing. You have n equal to m1 to m2. You have representations which take value in this field, and then you have some derived version that I will explain in an example, which is a map from H. And here you have an action of GLN, and here you have an action of the variable symmetric. And the claim is that in general we have some map from the GLN invariance to the tensor product, one-dimensional representation. It will be functions here. So this is called HC, so it's the Harish-Chandra and Harish-Chandra. Homomorphism. And again, sometimes it's an isomorphism, sometimes not. For instance, it is an isomorphism if you take polynomials in one variable. If you take polynomial in one variable, then you have only something in degree 0, and it means that invariant functions on matrices, here invariant functions on matrices is the same as the same invariant functions on diagonal matrix. Because generically you can diagonalize matrix. Now let's state the conjecture on this example, and I would like to deduce from this conjecture a combinatorial kind of identity, Macdonald type of identity. So conjecture formulated to the first four authors. So it is, that's what in example 3. So then it's HC. So if you want some intuition behind this conjecture that then you wouldn't believe it. So if a pair of commuting matrices, then up to conjugation, they are diagonal. Of course, the whole point is that this is not true. It would be difficult with commuting schemes exactly. It's not true. But in this derived world, it looks like it is true in this sense. And so what does it mean? It's so in this case, we'll have H1, so one-dimensional representation. My construction is just C as one by one matrices, and the differential is xy minus yx, which is here. So this is easy to describe, and then so the claim is that then H of AN would be isomorphic to functions from the diagonal matrices y1, y1, and all the variables θ1, θn, and invariant under the simultaneous permutation of these three sets of lines. Okay, so if you believe this conjecture, then what you can do is whatever the consequences. First of all, that you have the H the GLN invariance equal to 0. I is bigger than n, and this we can prove with other methods. So a priori, you can go up to n squared because you have theta ij odd value, which are degree 1. But it's actually, and then we can let a torus act on this and compare all the characteristics. Compare weighted all the characteristics. For a torus action. So x y must 1 x. Like theta will go lambda. So everything is equivariant for these actions. We have two groups elements rather than you can multiply it in this way, get a torus action, and then you can look at So then you can decompose into degrees for this action, and write the generating function. Very clear, and of course you don't need to know the cohomology to compute the other characteristic, because the other characteristic of the complex gives already the other characteristic of the homology. So this you can compute at the level of complex. So let me write this conjecture in kind of suggestive way. There's different ways. This kind of comparison. There are different ways to do it, but there is one which I think is nice because it generalizes to other groups, other algebras. I'm not sure I will get to gauge theory, but anyway, here there is a nice formula which is this 0.2. So let's say N will be the sum of we take a part of degree AL, we want to take the generating series of dimensions of weight spaces for this torus action. We have to show that the torus action can be defined, but I think that's so we get an identity for the conjecture. It's the following identity. So let be equal to the unitary group and W symmetric group, and then you have the DG, the half measure. Integral normalized to D1. Like this. The left hand side, the cohomology of the representation scheme is written in this way. Okay. We should think of expanding this in powers of Q1 and Q2. This is the adjoint action of a group element on the algebra. And this is equal to a similar expression, but for the Y group. You divide by n factorial. Okay, so this is the identity, and so this is a consequence of the conjecture, but we can actually prove this identity independently. So I don't know. So I wrote it in this way, but here this integral over G you can reduce, since it is a invariant function, you can reduce it to an integral over a torus. So over the torus G, and then you can, I mean, this is the form it appears when you start counting dimensions. But this is suggestive because you can ask, is it true also for other compound groups? And right, so maybe I have to several remarks here. First remark is that so we conjecture for all compact connected groups And this follows from a conjecture, the algebra version of conjecture. Then, so this is proved. Well. And the way you prove it is to prove this follows from the HC conjecture. The conjecture that this is an isomorphism for the quantum plane. If you deform your commutative algebra into this infinite data, which is not a root of unity, then you can compute this and prove that you have an isomorphism. In fact, everything goes into the zero homology. You can check it, and then you show that the Euler characteristic is independent of theta. But for theta equal to 1, then the homology starts to spread in all degrees. And then there is a rule. Rank smaller than 2, and including for G2, right? So at least gives us some confidence. Works even for exceptional groups. So this for G2 would be an explicit calculation by summing all residues. And rewriting in this way, and it was done with a computer by a student, Willwacher. And I hope it's right. I didn't check the code. At the end, I saw that some equal to 0 came out for the difference. Okay, so right, maybe the next. Right, so there is here one question that that was answered by D'Alessio, is that we have this explicit resolution, and we see that on the resolution we have a torus action. The torus action leads to the resolution. But what if you take another resolution? So D'Alessio was able to construct to make this more precise in the sense that he defined another category structure on DG algebras with an algebraic rational torus action, and then resolution. There is a resolution which is equivariant and independent of the choice of resolution. So it's some kind of well-defined state. And then the last remark is that the left-hand side is so a coefficient, coefficient of rank 0 training 0 version of the Nekrasov partition function. The Nekrasov partition function has some additional stuff in front, but basically it is like this. So we wanted to see what the partition functions appear. So this rank 0, of course, appears also in the theory of Nekrasov partition function. I think Eric is a specialist in this story, and so surprising that I would like to understand this story in terms of partition functions. So I don't know if I have time to say that. Probably not, because it's already. So the left-hand side would be here. This would be the other characteristic of the length of the complex, if you like, defining it, and this would be generating function of one characteristic of the right hand side of this. Right, so let me just say a few words because I think I'm out of time. So, we at that point we observed that this is similar to the Nekrasov partition function, and we had some found some relations, and then Derived in last year's paper he clarified this. So he has a version of this kind of construction starting from quiver, from algebras related to quivers. So quivers with relations, the relations are the moment map condition, which appears in Nakajima's quiver varieties. So he constructs such derived representation scheme for these algebras of, not algebras of quivers with relations. And then proves that the Euler characteristic under certain assumptions is equal to the corresponding K-theoretic Nekrasov partition function. And the assumptions are if moment map is flat, which is a kind of combinatorial, characterization in terms of dimensions of the quivers. And then you can also introduce matter fields, which corresponds in this language not to consider only the GLN invariant component, but all isotypic components. For each isotypic component, you have in the Nekrasov case, you have some kind of tautological bundle corresponding to the reducible representation. And the corresponding partition function is determined in terms of the Euler characteristic for the isotypical component. And this again, so it's under some conditions with large representation. Anyway, so this is clarify that, and here I will stop. Thank you.
Thank you very much. Other questions?
Do you know how to modify the construction to get the rock arm That's right, yes. So what you have to do to take is the quiver, the partagé quiver. So you take the quiver, you have this right, so you basically take this ADHM relations. This would be the partagé quiver, so this would be in this case the mark is 2, and then you take U inverse of 0 modulo the random categorical quotients, which would be the affine version with varieties, and then you can relate these to representation homology. The algebra functions here, and then the derived version will give you the rank R. You can also introduce push forward of tautological bundles by taking not the invariants but the isotypical components.
So both of these slides are really characteristic of some algebra. But the question is there an interpretation in terms of partition function to the right hand side?
I don't know. Right. So you know, I mean, this formula smells like a localization formula. Correspond to fixed points. And so here I don't have such an interpretation. In the case of the class of partition function, when you take rank R, then you have two expressions. One expression is an integral formula, and the other is the one that's the class of K, which is a sum over partitions and stuff like that. So it is similar, and that one is defined similar in the sense that you have an integral equal to some sum, but it's not like this.
It's not the same sum there.
It's not the same sum. No, I cannot relate it. And also, I don't have such a conjecture in the case of rank R, in the case of partition function K.
Are there questions from the online audience? Please just no questions, then let's thank Giovanni once more. Dans notre tradition, il y a un dîner avec le conférencier. Sponsorisé par l'Institut. Si vous souhaitez vous participer à un institut de moléculaire, vous les verrez.